Dorde. I'm currently protocol engineering team lead at Monad Foundation. Before that, I was a co-founder in DeFi, and prior to that, I was part of the core Solidity compiler team. You can find me on X. I'm the most active there. About Monad. Monad is EVM compatible, decentralized, high throughput L1. It has some small differences, and it has some significant improvements to the EVM, including asynchronous execution, different BFT, and customized DB. Currently, there is a 200 active set of validators, which will increase to 300 soon. It has 400 millisecond block times, which will decrease even further soon, and 200 million block gas limit, so it can achieve up to 10K TPS. Some significant improvements that are coming soon is pagified Merkle-Patricia trie, which is the topic I will be discussing today. Encrypted transactions. Because of asynchronous execution, you can keep transactions encrypted until they are executed. So some parts of MEV will be wiped out. And as I said, we will be increasing active validator set further. So I'm going to use this contract as an example for storage across the presentation. So it has a couple of state variables and one array. What does compiler do in this case? So slot 0 is first variable, slot 1 is packed with the second two variables, and there is some empty space there. The third slot holds the length of the array, and the data of the array is located at catchup of 2, which is somewhere further away. And this was done mainly to reduce the chances of clashes. So, yeah, what is Merkle-Patricia trie? So every Ethereum account has these 4 things: nonce, balance, code hash, and the storage subtrie root. What we will be talking here is the fourth part. It's basically the root of Merkle-Patricia tree, where slots are actual leaves in the trie. And the database itself is key-value pair. These slots, the keys are calculated basically with the hashing of the contract address and the slot. So what it does actually, what happens is the database is having slots that are next to each other in very different places because they end up with a completely different key. And this is how, for this contract, the trie would look like this, and you can see that there's no any kind of sorting based on what compiler is doing with the slots. So it's basically random. So that led us to, and the main reason we thought about MIP8 was that localized data is why it is important. First of all, every new modern hardware, when you load one storage slot, it loads 4 kilobytes of data because that's how hardware actually works. So it loads additional 127 slots that are probably completely random based on your implementation of the database. So in order to improve that, we designed MIP8. You can you can check the Okay. So you can find the implementation or the details about the MIP, including like all the gas costs related to it and the plan for like how do we migrate the whole database. So what it does is it packs 128 slots into single page and keeps that page as a leaf in a Merkle-Patricia trie. So whenever you load one slot from that page, every other slot is going to be warm. So whenever you access slots that are next to each other, you're getting warm S loads. This effectively means that like whenever you have localized data, you get everything else with no additional cost. And that's how hardware operates, and this is now aligning more closer to that. So you can get the page index by shifting the slot to the right by 7, and the offset is basically what exact slot you are having in the actual page. So since this change introduces quite a nice tool to optimize contracts, it would be very nice to design storage with this in mind. So I'm going to show now how does page look like for the same example we had. So first page would contain first 3 slots from the contract, and an array was basically is ending up in the page where 78 slots are empty at the beginning, and then there are elements of the array. This is not so efficient because you're wasting basically these 78 slots, and you can only fit 50 elements in the first page. So whenever you go over 50, your excess, like if you are iterating over an array, would load more pages. And there's one more thing as well. The length itself is disconnected to an array, and most of the times you access both length and the data at the same time. So this is how it looks like. For push and pop, it's 2 called storage access. And for iterating over 127 elements, in this particular case, is 3 pages, because one for length, second one for first 50 elements, and the third one for the rest. And yeah, this is still better than compared to like 127 plus 1, which is 128 cold storage reads. So what can developers do to optimize this even further is place the length together with the data and align the starting slot of that data to be page aligned. So how does it look in that case? Its push and pop are always 1 or 2, depending on the array length. Whenever array goes over the first page, it will be 2 called storage access. And iterating over 127 elements is 1 called sload, because the whole array fits 1 page. And the implementation of this particular array can be found in monad.std library, and we are going to follow up with more data structures along. So yeah, what I just explained, it looks like this now. So on the right side, you can see the array is being page aligned, and all the data is together. So there's one other example that I've seen across many contracts, and that's people are used to having a lot of mappings that are mapping from the same value to some different, like in this case, let's say there is balances mapping and available mapping. What compiler does under the hood, it uses catch-up of the slot where mapping is reserved, and the key, it hashes it together and places the value in that particular slot. So basically, these two things would end up very far away. And if you are accessing both at the same time, you are getting two called as loads. So how to fix it is use a struct, back the data, and map only once. Then you are getting data that is localized. Probabilistically, it depends like how big your data is, but there is a chance that it can end up in the same page. And we are also going to write a custom library for mappings as well, so they are also page aligned. Some benefits and unlocks of this. There was a team in the ecosystem, an order book, that updated their contract logic to be page aligned, and they got around 10x improvement for gas costs in order settlement. So that's quite a lot, and it means a lot for market makers that are going to do place and cancel a lot of orders at the same time. Basically, contracts that use large chunks of data, like matrices or arrays, which is basically, it unlocks on-chain inference, where you can store an AI model in storage, directly load it, and do some inference on this data, which is interesting use case. We will see how it is going to be used by the ecosystem. And basically, any contract, if you use normally, like if you have a couple of storage variables at the beginning of the contract, they will all be in the same page. So of course, if you design the storage for MIP8, you are going to get additional benefits. But any contract today will get improvements. So next steps for this work would be implementing more data structures, like linked lists. Currently, I've seen different implementations of linked lists, but most of them are using mappings, which scatters all the nodes across. So we are going to try to make it localized. Queues, trees. Trees are very interesting because a lot of order books are actually using trees. I'm currently working on designing syntax for custom storage layout in Solidity. And yeah, I'm trying to find the proposal that is going to work together with what was already explored by the team. And potentially, this will be contribution from us back to the compiler, which is one of the goals of our team, protocol engineering team at Monad Foundation, also to contribute back to Ethereum research. And that's about it. We have 10 minutes for the questions. I planned it. Cool. Yes.
Hi, hello. So regarding the gas cost, actually my question is, so it exists for a reason, and I assume when you say that there is a 10x gas cost improvements, so on the side of the EVM, the performance increase should be like pretty much the same. So is it true or not?
The question is performance. Is it like if I didn't get what was the question?
I mean, basically, the gas cost exists to limit like the amount of transaction. Basically, no, we can think about it in this way. So and when you increase the throughput, basically by decreasing the gas cost required, you mean that you have to increase your power of the computation power, basically.
Yeah, but the main unlock here is when you load the data from hardware, you're loading 4 kilobytes of data, and everything inside the data is already, inside that block is loaded. So if you localize the data to use it like that, gas costs are the way to, like they should be showing how much effort does a validator need to execute something. So if it's warm load or cold load, they are there for a reason. Because if it's warm, it's already loaded. If it's cold, you need to get it from the disk.
Yes, so basically this paged load is basically more efficient on the validator side. On the
Yeah, it's how hardware works. Basically, you cannot get one 32 bytes
I see.
or whatever else. You are getting 4 kilobytes.
All right. And when we speak about the existing contract, so if we do implement the thing, for example, for Ethereum, so this loading of whole chunks of data, will it be still like feasible on the large existing contracts with existing storage layout structure?
Well, the existing contracts will still work. If they didn't use any optimization that would localize the data, then they will not get the optimization. But what I was saying is, if you have like uint A, B, C, when you load A, you loaded everything else for your contract. But if you have used quite a lot of mappings that are mapping from the same value to few different values, you are getting nothing. So all of the access would be cold. Sorry.
Yeah, I see. But will it be cost hardware-wise like the same? So meaning
it will stay the same for the old contracts. It's a little bit cheaper when you have some parts that are already preloaded, but it will be kind of similar. But the costs are going to stay also similar without optimizations.
Nice. Okay, good. Thank you very much.
So I want to ask about contracts that are already deployed. So let's say that go into Monad right now and deploy a smart contract, and you finalize this proposal. Is it possible to recompile the Solidity smart contract that I have already deployed and then get the optimization after that? Or is the actual data use going to break the contract because I change how things are stored? Is it possible to retroactively use it or not? That's the question.
That's a good question, but unfortunately it's not, because that would require some mechanism for upgrading the contracts with a different code, and I'm not sure that's something.
Okay, but if that's available somehow, is it possible to do it technically?
Technically, probably it would be possible that you migrate the data somehow, but I don't think this will happen in any time soon.
Thank you.
Thank you all for your question. I'm sorry we have to cut it here. Give a round of applause to Dorde, and let's get ready for our next speaker.